In this lecture, we will be discussing about micromeritics. What is micromeritics? And we will be discussing about few of the fundamental properties of powder particles. This lecture includes the introduction to the fundamental properties of powder or the particles and a detailed information on particle size measurement is given in this lecture. Let us discuss about the introduction. Micromeritics. Micromeritics is the study of particles. Now, why is it necessary? For a pharmacist, it is necessary to study the particle sizes and particle size distribution. Micromeritics includes the study of fundamental and derived properties of particles or powder particles. Now, whenever we say the study of powder particles, it could be an individual particle or it could be aggregate of particles. Aggregate of particles are normally known as granules. Now, in this picture, we are able to see the scanned image of a powder like magnesium powder is taken, and this is a scanned image. In this image, we are able to see each powder particle, magnesium particle. Now, if we consider this particle, now it has shown 50 micrometers as its diameter under this scanning electron microscope. Now, from this microscopic method, we are able to see the shape and the size of the particle. Now, in this chart is taken from the textbook of physical pharmacy by Alfred Martin. Now, this is for illustration of the particles having different particle sizes. Now, if we see from this, we are able to see the microorganisms having different particle sizes. Size range of micrometers is given. Now, here, these are the various microscopic techniques like white microscopic technique, UV light microscopic technique, ultra microscopy, electron microscopy. These are the various methods or the techniques by which we can study the particle size of different ranges. And the most finite particle could be evaluated or observed under electron microscopy as it ranges from 6 to 0.001 micrometers. So these are the various techniques, laboratory techniques by which we can evaluate the particle sizes. Now, is it really important to study the particle size for a pharmacist? And how far this micromeritics is useful for a pharmacist in the formulations? That we are going to see now. Let me give one example. Suppose, let us consider formulation of inhalations. Let us consider this. So inhalations or the inhalation powders are used to treat most of the upper respiratory tract infections or even the lower respiratory tract infections. For example, let us consider the inhalers used for asthma treatment. Asthma treatment. Now, in these inhalers, we will be making use of drug powder. Drug as powder is used. Now, we being a pharmacist, we should be really careful enough to formulate inhalation having powder particles of specified particle size. Suppose if the particle size is greater than the specified, it would obstruct the bronchioles. And if the particle size is much lesser than the specified range, then there is a chance of escape of the particles into the air when we are pumping the inhalers rather than getting into the oral cavity or the nasal cavity. There is a chance for the particles to get escaped into the atmosphere because of its very fine size. Hence it is really important for a size to be determined and maintained in case of formulations, especially for inhalations. And even in the formulations like suspensions and emulsions, the particle size or the globule size plays a major role in improving or in sustaining the stability of the formulation. Now let us get into the details of the properties. Now we are studying the particle characteristics. The particle characteristics are being classified into two categories: fundamental properties and derived properties. Derived properties include porosity, bulk density, Hausner ratio, Carr's index, which are very important for a pharmacist during the formulation of various dosage forms. Now in this lecture, we will be discussing about fundamental properties, which include particle size, particle shape, particle volume, particle number of particles present in the given sample, particle surface area, what is the surface area of each particle, and how can we determine all these properties. We being a pharmacist, we need to make sure that we should know how to determine the properties of the powders before we start with the formulation. Now let's get into the fundamental properties of particles. Now here in this chart we are able to see the different pharmaceutical dosage forms having particles of different size ranges. Mostly the suspensions and fine emulsions, they share the particle size of 0.5 to 10 micrometers. And the flocculated 10 to 15 micrometers, like that. So this is a basic chart that is taken from the textbook of Physical Pharmacy by Alfred Martin. Now let's get into the details one by one. First, we will be discussing about particle size and particle size distribution, and also particle number. How can we determine the particle size, number of particles in a given sample? Now let's see different methods available. Now we are discussing about particle size determination. Is it really important, and how it is important for a pharmacist? To determine particle size of the given powder sample, we are having three techniques. The first one is microscopic technique, second one sieving technique, and third one sedimentation technique. There are many other techniques which we are going to see now. Now, few techniques are used for the particles having a specific size range. For example, optical microscopic technique is applied for particles having particle size range of 1 micrometer to 100 micrometer. Electron microscope is used to determine, it is very sensitive and it is used to determine the particle size range from 1 micrometer to 10 angstroms. Sieving technique is used for a range of 10 micrometers to 1 centimeter. Sedimentation technique is used for a range of 1 micrometer to 1 mm. Likewise, based on the size ranges and specificity, we will be having a specific techniques to get precise results. Now let's get into each technique. The first one is microscopic technique. Mostly this technique is used to study the particle size range of 0.2 to 100 micrometers. Now let's see microscopic technique. The name itself indicates we will be making use of microscope. It could be optical microscope, and based upon our part of sample, we can make use of electron microscope. But for today, we will be discussing about optical microscopy that can be easily carried out in a laboratory. Now for this optical microscopic technique, apart from the microscope, we need to have stage micrometer and eyepiece micrometer. We need to have stage micrometer. Now, in this figure, we are able to see the microscope. This is the stage micrometer, and this is the eyepiece micrometer. Eyepiece micrometer is available in different graduations. It will be having small, when we look onto this, we will be able to see graduations, scale divisions. Now we'll see in detail how it works. Now this is the stage micrometer, and this is the area where we'll be able to see small scale divisions. So one division is equals to 0.01 mm, right? Now if we keep this slide, this is known as stage micrometer, and this slide is to be kept on this part. This part of the microscope is known as stage, right? So we will be placing this stage micrometer here, and we will be choosing any one of the eyepiece micrometer based upon our specifications, and we will be placing this eyepiece micrometer here. Here this is detachable, and this here we will be placing our eyepiece, and we will be covering it up with the eyepiece of the microscope. So when we look from here, we will be able to see the graduations or the scale divisions on the eyepiece, and we will be able to see the graduations on the stage micrometer. Now we are already having the stage micrometer here, and the eyepiece micrometer here. So when we are seeing from the eyepiece, we should be able to see the graduations of both the eyepiece micrometer and the stage micrometer. Before we start with the experiment, we need to calibrate these two micrometers. How can we calibrate the micrometer? It is very simple. Now in this, we are seeing, suppose if we are observing under the microscope through the eyepiece, we will be able to see the eyepiece micrometer graduations like this and stage micrometer graduations like this. Now before we start with the experiment, we need to actually observe or actually calibrate the instrument, just like we do for other instruments during before experimentation. So how can we calibrate this one? It is very simple. We need to actually move the stage. How can we move the stage? Here we are having now here we will be having some knob where we can move the stage to and fro. We need to adjust the stage micrometer in such a way that the graduations or the divisions should overlap with the divisions of the eyepiece micrometer. So we need to adjust the stage micrometer by moving the knob of the stage of this microscope so that the graduations should overlap like this. So it should coincide like this. So then, thus the calibration of eyepiece and the stage micrometer is carried out. Now, our next step is soon after calibration. Now, this is how we will be seeing the stage micrometer. See, each small division is equals to 10 micrometers. Each small division, see here, we'll be able to see each small division is equals to 10 micrometers. Now, we are done with the calibration of the instrument. Now let's get into the actual procedure. Now we are given a powder sample for which we need to determine the particle size. Take the powder and make the powder as a suspension by adding a vehicle in which the powder is insoluble. It should not make a solution. You should prepare a suspension. So you should make sure that you need to select a vehicle that in which the given powder is insoluble. Now thus we get a suspension. That suspension, a drop of that suspension is taken over the slide and it is observed under the microscope. Now the eyepiece of the microscope is fitted with the micrometer. That is already done during the calibration. So we are having a slide on the stage with the sample and we are observing the slide through the eyepiece which is having micrometer. Now all the particles are observed through the microscope and we need to just move the slide and count the number of particles. Now for example, if we consider this slide, this micrometer is having divisions like this. Now the particles, let me explain this way. If we consider this micrometer now, and this is the slide where we have taken particles suspension, and through the micrometer, an eyepiece micrometer, if we observe all the particles, the view would be like this through the micrometer. So we can now count the number of particles that are present in each grid. We need to make an observation table having like this. So the first column represents the first grid. How many number of particles there? If there are 2 particles, 2, we can write 2. And second grid, if there are 4 particles in that, we can write 4. That's how for the given sample we can make a note of number of particles present. So when we sum up all these particles, that gives the number of particles. And this data is very much useful in uh, like in preparing a data from which size frequency distribution curve is obtained. We'll see what is size frequency distribution curve. Now from this we will be able to see the number of particles, and also we can determine the size of the particle, because from the stage micrometer, which has divisions like this, from the micrometer each division, and from the stage micrometer we will be able to see each division is 100 micrometers. Now this is the image of a particle or the object. Now if this particle has occupied 5 divisions, so you can easily say the size of this particle is 500 micrometers, because each division itself is equal to 100 micrometers. That is how we can determine the particle size, like how many divisions the particle is being occupied. And that is how we can determine the particle size and the number of particles by this optical microscopic technique, especially with the use of micrometer, stage micrometer, and eyepiece micrometer. Now this is a bit tedious. Now to avoid such few errors and counting of the particles, because when we are viewing the microscope and at the same time parallelly to note down the observations, it'll be little bit difficult. So in order to avoid that, the microscope can be projected onto your screen or photographed for the later measurements, for for the further measurements. So in sophisticated microscopic technique, we will be having this feature where the microscopic observations can be projected over a screen, or that even connected to a computer screen. So this method is most widely used in the laboratories. This is the method where even the particle number and the particle size distribution can be obtained. Now let us see what are the disadvantages and advantages. So disadvantages, it is quite evident that this process is very much slow and very tedious. We need to at least count 300 to 500 particles size to get precise data, to get the average data. And in this method we will be able to measure the length and the diameter. The two-dimensional technique, this is a two-dimensional measurement technique. And most advantageous thing of this technique, microscopic technique, is we can measure the particle size of no, each individual particle and also group of particles. Group of particles, nothing but the agglomerates, can be easily known. Now, let us see how can we analyze the mathematical data that we get from the microscopic technique. From the microscopic technique, we will be getting the information about the diameter of the particles and the number of particles, right? Suppose from this data, we can analyze that there are 4 number of particles having 10 micrometer diameter. There are 7, similarly there are 7 number of particles having 20 micrometer diameter, like that. So like that we will be getting a series of data. Now how can we analyze this data and get the mean particle diameter or the mean volume, surface diameter? Here we need to make a tabular column like this. The diameter d, number of particles n. From these two columns we need to derive few other parameters. The next one is nd. We need to multiply this column n into d, n into d. And next we need to make sure we need to have d square values. Next n into d square values. Next d3, d cube, d3, d cube values. Next nd cube values. Now what is necessary to do all this d square, d cube values? Is it really necessary? We need to consider the 2-dimensional, 3-dimensional, the size of the particle. Hence we will be considering the d square and d cube values. Now sigma, whenever we come across the sigma, it represents the summation. Sigma n represents the summation of all the values. 4 plus 7 plus 3 plus 2. Sigma nd represents the summation of all these values. Similarly, sigma nd square summation, sigma nd cube summation of all these values. Now let's see how can we use this data in getting the mean particle size. The mean diameter is equals to the length number. It is also known as the length number mean diameter. We are considering the only one dimensional length wise. So it is only d we will be considering. Sigma nd by sigma n. Sigma nd by sigma n is equals to 21.87 micrometers. So this is the mean diameter, one dimensional mean diameter. And let's consider the volume, the mean diameter by considering the volume. The volume itself says we need to consider the 3-dimensional length, breadth and height. So we will be considering 3 times of the value, that is d cube. So sigma d nd cube by sigma nd square is equals to this. This is how we will be calculating the particle size of the given powder sample. So this is about the electron microscopic technique, where we will be getting a data by using stage micrometer and the eyepiece micrometer, and thus we can calculate the particle size and the number of particles present in the given sample. And the next technique will be sieving technique. In this technique, we will be making use of standard sieve set. The name itself indicates we will be making use of sieves. So the principle indicates sieving or sifting. So it is a very simple technique, and in this technique we will be able to determine the particle size and also size distribution, and also weight distribution is easily obtained and calculated. Now let us see how this method can be carried out. It is a simple technique which makes use of sieve shaker. This is known as a mechanical sieve shaker. This is a plate, bottom plate. This is the top plate, and this is the knob. When we turn this knob, we can adjust the height of the lid. Now we need to rotate this knob, lift this plate up, and place the standard sieve set here according to the number, sieve number, and close the top with a lid, and again tighten these knobs. Now this is how we need to set the sieve shaker. This is a mechanical sieve shaker, and we need to set all the sieves here like this. This is a monitor with few setting systems where by which we can set the number of tappings or the time for this equipment to run. Say for example, if we set this equipment for 20 minutes, now this equipment will be running for 20 minutes. Now let us see how this actually works, how this instrument is used for pharmaceutical purpose. Now here we will be having a set of sieves having different numbers. From this diagram, we will be able to see sieve number 5. In some sieves, it is given as mesh number 10, mesh number 35, see 60, 120, 230. The sieve number indicates the number of pores per square inch. Very simple. Sieve number indicates number of pores per square inch. Means lesser the number, greater the pore size, and lesser the number of pores. You understood? Now suppose this is the larger mesh. Suppose let's consider this one. This is mesh number 5, which indicates 5 pores per square inch. Say suppose this is the square inch. So if we are discussing about a sieve number 5, now the square inch should have 5 number of pores, right? 5 number of pores means larger. So this is sieve number 5. Now suppose consider sieve number 10. This is the sieve per square inch. 10 means 10 circles. Sorry. Kindly bear with my drawing skills. So sieve. So means what here? This mesh is able to accommodate 10 pores per square inch. This able to accommodate 5 apertures per square inch. Means what here? As the sieve number increases, number of pores increases, the pore size decreases. So now we need to arrange the sieves in such a way that the top portion of the sieve should have the larger pore size. So the lesser mesh number or the sieve number should be on the top, and the greater sieve number should be at the bottom. So the larger mesh and the very fine mesh, fine pore sized or aperture sieve should be placed at the bottom. So when we place powder sample on the top and when we switch on this equipment, suppose on the top we have added powder sample, we have closed it and we switched this on. So now how this works, this is known as a mechanical sieve shaker. The name itself indicates because of mechanical movement to and fro, because of these agitations or movements of to and fro, the powder that has been put on the top mesh, because of these movements, the powder particles will get sieved through these pores. The larger particle size will remain on the top mesh and the lesser particle size will be on the second top mesh. Likewise, all the particles will get sorted by their particle sizes. So when we go on to the bottom of the sieve set, because of the very fine pore size, we will be able to get the fine powder at the bottom. At the bottom of the sieve here, we will be placing a pan where the bottom layer is collected. So at the end of 20 minutes, we will be able to separate the powder sample based on the particle sizes. The top mesh will be having greater particle sizes and lesser, the second larger particle size. Likewise, we will be able to separate the given powder sample according to their sizes. So in this, we will be able to determine both the particle size and also the weight of the particles having the same particle sizes. Suppose if we have taken 50 grams of 50 grams of sample here, and after experiment at the end of 20 minutes, take out the sieve, separate the powders, at the end of the experiment, separate the powders from each sieve and weigh it and weigh and weight and weigh each sample from each sieve. So we will be able to get the percentage weight sharing the particle size. Now how can we determine the particle size? Now here we are able to differentiate how much amount of percentage. For example, say 50 grams, out of 50 grams, so if we weigh, the first one is 10 grams, say 10 grams. So what is the weight percentage? 10 by 50 into 100 gives the weight percentage on this mesh. Suppose this is 2 grams. 2 by 50 into 100, 2 grams by total weight into 100, as we are taking as a percentage, gives that percent of that amount. So from this we are able to determine the percentage weight retained on each mesh. How can we determine the particle size then? It is based on the specifications. Let us see. It is a standard one, very easy. This technique is really very easy. So actually this specifications of each mesh, according to USP is United States Pharmacopoeia, Um, USP gives us a standard information about the sieve numbers. Say for example, sieve number 8, the mesh, the aperture or the particle size retained on that mesh would be 2380 micrometers. Likewise for sieve number 10, like this. So when we look carefully, because of the greater pore size, the particle retained on that greater larger mesh would be of course a larger in size. The particles retained on the very fine mesh would be of course very fine in size. Here we need to know about two terms. Let us see what are those two terms. When we are considering especially a sedimentation technique or sieving technique, we need to know about two terms known as undersize and oversize. The name itself indicates, suppose if we consider we have taken a powder sample and this has been set up to a sieve shaker. Now some powder will be retained on the mesh. Observe carefully, retained on the mesh, and some will be passed through the sieve number 10 and it enters into 35 number mesh, right? After that, some will be retained on this and some will be now moved on to the next one. Now this, the particles that are retained on the mesh are said to be oversized particles for mesh number 10. Undersize, for example, the particles retained on this, okay, and some amount will be moved on to this. So the particles retained on this would be considered as oversized because it is not being passed through this mesh. So it is known as oversized for mesh number 35 and undersized for mesh number 10. To no, to put all this in a nutshell, it is very simple. The particles retained on the mesh would be oversized for that particular mesh number because it is not being passed through the mesh, so it is oversized. Simple. And so the particle from the mesh from which it has been passed, that mesh would be called, that particle would be called undersize. It is of lesser than the pore size, so it has passed through the mesh, so it is known as undersize. Now let's see this one. Now let's consider the oversize undersize from this diagram. So these are the particles. Now this particle is said to be oversized for this mesh number. This particles is said to be oversized for this mesh and undersize for this mesh because it has passed through this mesh, so undersize. But these particles cannot be passed through this mesh, they are retained, so the oversize for this mesh. That is how oversize undersize plays a we can determine the oversize undersize particles from this method based on the size ranges. So based on the standard sieve number and the mesh size or the aperture size, we will be able to determine the particle size. And this method is described in a detailed way in the practical session. Let us see the advantages and disadvantages of this method. Advantages include This method is really inexpensive because sieve shaker and sieve set can be easily obtained and can be easily uh, conducted in the laboratory. And this method is very much useful to determine the size that ranges between 50 and 1500 micrometers. The disadvantages include below 50 microns, this is not possible. This method cannot be much used because we'll not get precise data. And we should make sure the powder sample that we take for this experiment should be very much dry. If it is having some moisture, it might clog the apertures, it might clog the mesh. And during the mechanical shaking of the equipment, the particles present in the powder might collide with each other and might cause size reduction because of to and fro motion of the vibratory shaker. So there might be a chance of particle size reduction, and there might be few errors because of that, particle size reduction. And because of this particle movement, as the equipment is under vibrations, the particles, because of this attrition between the particles, when the particles collide with each other, there might be a chance of size reduction, and also at the same time there might be a generation of electrostatic charges over the particles that might uh, lead to attraction between the particles and might lead to aggregation of the particles. So here the particles cannot remain as individual entities, rather it might cause lumping up of all the particles, or the coagulation or the agglomeration of all the particles might be seen. So this could be added as a disadvantage. So these are the advantages and disadvantages of sieving method, by which we can determine the number of particles, particle size ranges, and the weight distribution. How much of weight of particle is having a specific size range. And the third technique is the sedimentation technique. In this technique, the name itself indicates we will be making use of sedimentation as the working principle. Now, in this method, we will be making use of Anderson pipette as our instrument. Anderson pipette is an instrument used to determine the particle size and size distribution in the sedimentation technique. What is meant by particle size distribution? Particle size distribution is a mathematical data, the collection of data, which explains number of particles sharing specific size range. Just like in optical microscopy, we are having, suppose say 10 micron micrometer diameter particles. How many number of particles are sharing the same particle size? If there are 4, okay, 4 particles sharing 10 micrometer size. So here we are able to check the size distribution. How many number of particles? It's not just the number distribution, also size distribution. Number of particles having same specific size, like that. Now let us see what is Anderson pipette, how far this is useful in determining the particle size and particle weight distribution. This is the Anderson pipette. Anderson pipette has a vessel, cylindrical vessel. This is the cylindrical vessel. Inside the cylindrical vessel, we'll be able to see a pipette with a very narrow, aperture. And on this vessel, we'll be able to see graduations here on this vessel. On the top of the vessel, we will be having a reservoir for the sample, and this is fitted with a stopcock where we can turn this to let the sample inside the instrument. Now here, this inside the pipette is fitted firmly in such a way that the stem of the pipette should be inside this vessel, and it should be at least 20 centimeters. It should be immersed. Now in this vessel we'll be taking sample, and the pipette is to be placed inside this instrument in such a way that the stem should be immersed to a length of at least 20 centimeters. In other words, the lower tip is 20 centimeters below the surface of the suspension. Now this is about the construction of Anderson pipette. Now let us see the working principle of this Anderson pipette, how this is used to determine the particle size. Now as the technique itself is known as sedimentation technique, here we need to consider our Stokes formula. And it's time to brush up your minds to remember the sedimentation of suspensions. Let us recollect the basic principle of sedimentation. Let's see the steps of procedure. How can we use this pipette? Now this is the Anderson pipette, the cylindrical portion, which is a graduated one, and inside we are having a pipette, and we should make sure that it should be at least 20 centimeters, the pipette. And here it is a stopcock where you can close it soon after the sample is filled inside. Now just like in our optical microscopic technique, we will be making use of the sample in the form of suspension. The given powder sample is made into a suspension like 1% or 2%. Like if you are given a powder sample, take 1 gram in 100 ml of some medium in which the powder should be insoluble, and we need to add a deflocculating agent. We should make sure that the suspension should be deflocculated because it should remain as individual particles. Then only we can be able to determine the individual particle characteristics. So the medium we select should include deflocculating agent. By means of some electrolytes, we can promote repulsive forces, and thus we can make deflocculated or deflocculating agent. Now the suspension that is made as a deflocculated suspension is introduced into this vessel. Now the vessel is stoppered, means it is so that the sample remains inside this vessel. Now this cylinder is shaken to redistribute all the particles. This shaken, and then this is kept in a constant temperature bath just to maintain constant temperature. Now, we being a pharmacist, we should make sure that at regular time intervals, the sample is taken by means of pipette, like 10 ml of sample is taken out into a china dish. 10 ml of sample is taken out into a china dish. Now let us consider this one. Suppose this is your Anderson pipette, vessel. This is your pipette. Imagine here you are having suspension. At regular time intervals, 10 ml of sample is taken in a china dish and is subjected to evaporation. Now, as soon as you take out the 10 ml sample, make sure that the deflocculated or make sure that the suspension level is maintained by adding deflocculating agent inside. So at regular intervals, you repeat the same thing, like take out the 10 ml in a china dish and heat it. So whenever we take out the samples, we need to refill it again with the deflocculated, and just to make sure that there is no change in the concentration of deflocculating agent. Now heat these china dishes at regular intervals, and after all the medium gets evaporated, we will be left with only solids. Now weigh each sample at regular time intervals. Now we need to consider Stokes' law or the Stokes equation. We already have Stokes equation. Rate of sedimentation is equals to sediment volume or the sediment height by time. Also, by considering this formula, d square into rho s minus rho naught into g by 18 eta. If we recollect our previous suspension and sedimentation volume parameters, how can we make use of this sedimentation technique in determining particle size? From this formula, it is very easy for us to determine it. The rate of settling sediment height by time, particular time interval, is equals to the sediment height by time interval is equals to d square diameter of the particles, which we need to determine, into rho s, density of the powder sample that we know, we will be knowing that, and the density of the medium which we use in the experiment, into g, that is constant acceleration due to gravity, by 18 eta naught. 18 is a constant, eta is the viscosity of the medium that we used in the experiment. So it is only this parameter that we need to determine, and we are having h by t, sediment volume by time interval, into the density of the solids, density of the medium, acceleration due to gravity, and the viscosity of the medium. So if we put all the values in this equation, we can easily get the diameter, d square value, like cross multiplication. So we'll be getting d square values, and from this we will be getting d value. This is how the diameter of the particle can be determined by making use of this technique. Now here From this experiment also we will be getting the values of undersize and oversize. How can we get it? Just like in our sieving technique, we can even get the information about the oversize and undersize. How can we get it? The undersize is the sample which we get which we get in this residue. This is known as undersize. So to be precise, so when this is kept aside for standing, so when we are taking out the 10 ml sample, we will be able to get the sample from this place, and during that process remaining particles will be undergoing sedimentation, right? So here the particles which are still undergoing sedimentation will be collected. Parallelly, there are few particles which have undergone settling sedimentation. So here, when we are taking of the sample in a china dish, that indicates it is undersize. And the particles which are already heavy, they have already got sedimented. Those are known as oversize. So from the sediment, we can get the oversized particles, and from the supernatant liquid, we will be able to get the undersize particle. So by adding all the samples that are collected from the china dish, we will be able to get the cumulative weight undersize. By adding up all the residues from the china dish we'll get cumulative undersize. Now this percentage cumulative undersize, when taken on the y-axis, we need to plot a graph. So when we are speaking about the physical pharmaceutics, it actually includes the interpretation of the data and also uh, graphical presentation of the data. So it is always very important to uh, project the details or the data in the form of graph. We will be taking cumulative weight undersize on the y-axis and particle diameter on x-axis. So particle diameter we will be getting from Stokes law. So the diameter will be taking on the x-axis, and the frequency is undersized according to the time interval. The first would be, for example, if say for the first instance, for the first 10-minute interval, we get 10 gram. 10 gram. For the next, we'll get 11 gram. Like this. We can take the data on y-axis and we can plot a graph. So we can get actually two graphs. So this is known as sigmoid curve. We'll be able to get the number distribution, how many number of particles, and also the weight distribution. The weight, like undersize and oversize. Now let us see the advantages and disadvantages. The apparatus is less expensive, and the technique seems to be simple, but it has its own disadvantages. It is very laborious. We need to take out the samples now and then. We need to weigh it. We need to check. So it is a laborious one. But at the same time, the results produced by this technique is very precise, very accurate, nearly accurate. But whereas for very small particles, this cannot be determined accurately. So these are the advantages and disadvantages of sedimentation technique. So in this lecture, we discussed about the fundamental properties of particles, and out of many fundamental properties, in this lecture we discussed about particle size and its determination methods. What are the various determination methods for the particle size? In that, we have microscopic technique, sieving technique, and sedimentation technique. Each technique is used for a particular particle range, size range, and they have their own advantages and disadvantages. It is for a pharmacist, it is very important to know which technique is used for which particle size range. So this is for this lecture. In the next lecture, we will be discussing about various other fundamental properties and their determination methods. Any doubts regarding this lecture? You can contact me through my mail. Thank you.